Hello, scholars. Section 2.2 is all about limits as they relate to infinity. So first we'll look at the limit of a function as x approaches positive infinity or negative infinity. And later we'll talk about functions whose limits are infinity as we approach a particular x value. So here to start this discussion, you'll have to draw in your own picture of y equals 1 over x. You could copy it from my slide here. You could copy it from your textbook. Notice we should have little arrows on the end here since this function does continue on. So as you do that, think about how you would go about making this picture if you didn't know. This function just missed being in your function booklet. You would try maybe plugging in some numbers. If we plug in 1 for x, 1 over 1 is 1, which is how we get this point here, 1 comma 1. You could try plugging in bigger and bigger numbers, and you'd have 1 over a bigger number, 1 over a bigger number, and you'd notice that your result, your y values, would be fractions whose denominators got bigger and bigger and bigger. Well, what's true about fractions whose denominators get bigger and bigger? If you have a half, a third, a fourth, a fifth, the denominator is getting bigger, but the actual value of the fraction, while still being positive, is going to tend closer and closer and closer to 0. So if you already understand that a little bit, the idea that as you plug in bigger and bigger values for x, you'll get fractions with bigger denominators whose values will become closer and closer to 0, you already sort of understand what we're going to get at here. I can say that as I let x approach positive infinity. So if I'm going to let my x values keep going, what happens to my y values? My y values with bigger and bigger denominators are going to get closer and closer to 0. So using this notation we've been talking about, I would say the limit of 1 over x as x approaches infinity is 0. I could try the other direction too. If I plugged in negative numbers, they got closer and closer toward negative infinity, I'd have a fraction with a negative value whose denominator got bigger and bigger and bigger, still would approach closer and closer and closer to 0, just that the value of the fraction would be negative, so you can see I'm approaching from underneath the line y equals 0. So, stop the video for a second, fill in the next picture on your table. You can use your calculator graph, you can make a table of values, and see if you can make a picture and think about the behavior of the function as x approaches positive infinity and as x approaches negative infinity. So I expect what you found is a graph with a similar picture, just shifted into a different spot. And for both of these graphs, the graph of y equals 1 over x that we made here, and the graph of 2x minus 1 over the quantity x plus 3, which you just tested on your own, you'll notice that there's a horizontal asymptote. Here I have a horizontal asymptote at y equals 0. Notice that is an exact match for the limit as x approached infinity of this function. If you took the limit as x approached infinity of 2x minus 1 over x plus 3, you would find a numeric value, and that would be the y value for your horizontal asymptote. So this is actually our definition for horizontal asymptote. Big idea here, the function has a horizontal asymptote at this horizontal line, y equals b, whatever b might be, if the limit as the function of the limit of the function as x approaches infinity is that b value, or possibly the limit as x approached negative infinity of that function is b. So down at the bottom of the first page of your handout, you can see another function that we've been asked to investigate. If you're having trouble reading it from your handout, I'm sorry, the copy is poor. You can see this is the function we're going to watch. So evaluating limits as x approaches infinity is a little bit trickier because you can't just plug in infinity. So we want to understand what that would look like to evaluate this limit as x goes toward infinity. So our one of the big ideas with this example is that unlike the last two pictures we just graphed, which each had one horizontal asymptote, it is possible for a function to have two different horizontal asymptotes. One asymptote that the graph approaches as x tends toward negative infinity, and a second asymptote that the graph approaches as x tends toward positive infinity. So we'll watch how that happens, and we'll start to think about what it would mean to plug in infinity. So if I want to investigate the limit of x over the square root of x squared plus 1 as x goes toward infinity. Imagine plugging in bigger and bigger x values. This little 1 down here, he has less and less and less and less power over the outcome as x gets bigger and bigger and bigger. So we could say that that plus 1 down there becomes insignificant as x tends towards positive infinity, which means algebraically we can consider a new expression, x over the square root of x squared. So just so now I can deal with this new expression. I can think of the limit as x approaches positive infinity of x over the square root of x squared. Well, if x is a positive number, the square root of x squared is simply x. So I can replace this expression, square root of x squared, with x, as long as I know that, and I do know that I'm just considering positive x values. And I have an expression that I can simplify. X over x, no matter what x is equal to 1. So I can conclude that I have a horizontal asymptote now at y equals 1, because the limit as x approaches infinity of x over the square root of x squared plus 1 equals 1. Now watch what happens as I let x approach negative infinity. So as x gets bigger, smaller and smaller towards negative infinity, this plus 1 still will have smaller and smaller and smaller effect. So I can change my problem to consider this limit as x approaches negative infinity of x over the square root of x squared. The difference here is that if x is a negative number, the square root of x squared isn't x anymore, because this radical symbol means to take the positive square root. So if I take a negative number and square it and then take the square root, I'm not going to get back the original number I had, I'm going to get back its opposite. So now I have the limit as x approaches negative infinity of x over negative x, which simplifies, when I divide a number by its opposite, always to 1. Now I know that there's also a horizontal asymptote for this function at y equals 1. And in case it comes up on your next test, because it will, let me show you how I'd expect you to justify that. I would say that there is a horizontal asymptote at y equals negative 1, because I'd expect you to write out, and to be able to write out, because the limit as x approaches negative infinity of x over square root of x squared plus 1 equals negative 1. So in calculus, frequently you'll be asked to justify your answer. You're always going to want to tie that justification back to a definition. So we know the definition of a horizontal asymptote is it's the y equals some value, where that value is the limit of the function as x approaches positive infinity or negative infinity.